We could look at this chicken and see a collection of zillions of atoms all moving around, incredibly complex. So we try and simplify it by drawing an imaginary box around the chicken and then looking for that one special point that kind of represents the mass distribution of the whole system, the sort of balancing point for the chicken, the point we call the center of mass of our chicken system, and then letting that one point represent the system as a whole. So suppose here we're looking down at a barnyard enclosure with two hens, a rooster, and a chick. And if we want to study the habits of these animals as they move around, we'd like to simplify things by replacing each animal with a dot to represent its center of mass. And then maybe laying down a set of XY coordinate axes here. And then our picture looks like this, with the dot for the center of mass of hen 1, hen 2, the rooster, and the chick. And then we just need to track the motion of these dots as the animals move around. Furthermore, we could look at the behavior of groupings of the animals by defining additional systems. So suppose we want to study the behavior of this hen and this chick together. We could imagine grouping them, calling that a system, and then finding the center of mass of that hen-chick system. It would lie along this line connecting the two centers of masses of the animals, and it'll be closer to the center of mass of the hen since the hen is much more massive than the chick. In fact, I think the center of mass of that system would probably be inside the body of the hen here, but there's nothing unusual about that. The center of mass of the Earth-Sun system would be inside the body of the sun, since the sun is so much more massive than the Earth is. Anyway, back to the farm. If you wanted to study the group of all four animals, you could call the whole collection of animals a system. That's our pink box here. And then the center of mass of that system would be a different point. That would be over here in between the two hens and the rooster, which all have much more mass than the chick over here does. Now, as the animals move to new positions, say like this, if the rooster moves over here and hen 1 goes there, hen 2 goes there, and the chick wanders over here, if they move to these new positions, then the center of mass will be in a new location. And so if the center of mass started over here and ended up over there, that means that that point had a velocity and it had an acceleration over time as it moved around. So we can track the position of the center of mass and its velocity and its acceleration just like any other moving object. We just need these equations to define this special point. So here are the equations you need to define and then track the motion of the center of mass of a system. First, you'll need to find the total mass of the system of n objects, just adding up all the masses. In summation notation, that would be the sum as I goes from 1 to n of m sub I, and we'll call that total mass the mass of the system, m sys. Then here we are, the definition of the coordinates of the center of mass of the system of n objects. The x-coordinate of the center of mass, would be like this value right here, is found by taking the weighted average of the x-coordinates of each object in the system. So mass 1 times its x1 coordinate plus mass 2 times its x2 coordinate, etc., and then divide the whole thing by the mass of the system. This is what it looks like in summation notation. So that's one equation where we weight all the x-coordinates by the masses of the objects. So the more massive objects carry greater weight and have a bigger effect on the outcome here. And a separate equation to find the y-coordinate of the center of mass of the system. Here we weight the y-coordinates of each of the objects by the masses of the objects. Then a very similar set of equations for the velocity of the center of mass of the system, where we just take a weighted average of the x components of the velocities of the individual objects to find the x component of the velocity of the center of mass. And separately, we take the weighted average of the y components of the velocities of the individual objects to find the y component of the velocity of the center of mass. And same thing for the acceleration of the center of mass, the weighted average of the x components of the accelerations and the weighted average of the y components of the accelerations. So if you've got those equations down, then let's apply them to a simple example scenario. We'll do just 1D here instead of 2D. So suppose a fox has gotten into the barnyard and is chasing the animals around. So if we're just running back and forth along an x-axis here, I've given you the x-coordinates of the animals' locations. That's in meters here, and the masses of the animals, and then above them in blue, the speeds and directions of motion for the animals. So use that information to calculate the following. First, the mass of the rooster, chick, hen, fox, hen system. Then the x-coordinate of the center of mass of that system, and then the velocity of the center of mass of that system at this moment. Pause the video, use those try out those equations. Ready? Okay, here's the results. Mass of the system is just the total mass. Check not just these values here, but this method against your own method. I want to point out here that the x-coordinate for the rooster is -2 meters, not just 2, but -2, because that's its x-coordinate. The x-coordinate for the chick is 0. And then in this equation, the velocity of the chick is -2 meters per second, since it's moving to the left. -2 meters per second for the chick. This hen is at rest, so 0 meters per second for the hen right there. It looks like our center of mass of the whole system at 4.3 meters is right about there, which looks pretty correct to the eyeball for this collection of beasts.